Hello friends, myself Chetan Jadhav. In previous lecture we have seen that the types of the elements, general steps in FEM. So today's lecture we are going to study the structural analysis of one-dimensional bar elements. So first of all we have to derive the equation for the structural analysis. So we are taking the one simple example, one spring. So now we can see we have to find out the stiffness matrix and global matrix for that spring. So one end fixed and other end we are applying the some pressure force, that is a P. So in that spring is having some stiffness, that is a K value, and which is having length capital L, and we are applying force at a free end that will be deformed, so that deformation is small u. So equation for that, so pressure is equal to K into U. So pressure is equal to stiffness matrix into deformation. So we know that the stiffness formula for the spring given is equal to force, that is pressure is equal to K into U. So same logic we are going to apply it to the find out the stiffness for a bar. So this is for one spring. So we are going to apply same logic for the bar. So according to the simple bar, at one end fixed and one end free. So now we can see the area of cross section of that part, that is the element number 1, applying force, pressure P, displacement small u, and distance L. So according to Hooke's law, stress is equal to E into strain. So stress is nothing but pressure upon area is equal to E is equal to into strain means U by L. Okay, change in length by original length. So rearranging this equation, so we will get P is equal to AE by L into U. So this is the equation number 2, and equation number 1, that is according to the spring, P is equal to K into U. So from this equation 1 and equation 2, we will get K is equal to AE by L. So this is the stiffness formula. From this first, from spring, we will get equation 1, that is a P is equal to K into U, and from this second simple one stepped bar, and from this we will get equation 2, that is a P is equal to AE by L into U, and from this two equation we will get the stiffness, that is a K factor, that is equal to AE by L. So we will take one of the example which is having two elements and three nodes, that is a element 1 and 2 which is having 3 node, and that 3 node having 3 displacement, that is a unknowns u1, u2, u3, which is having L1 and L2 length for a respective element. So from that we have to find out the stiffness matrix for the given problem. Okay, so what is the formula for that? The force is equal to K into U. Okay, so here I and J is a number of elements. So from this given problem, number of element is 2 and number of element node is 3. So K is nothing but your AE by L into 1 into minus 1 minus 1 1. This is matrix, stiffness matrix, into U, that is a UI UJ. So number of elements is 2 and number of node is 3. So we will find out the stiffness matrix for first element 1 and element 2 is equal to F force Fi and Fj. So this is the standard equation for this problem. So we have to find out the stiffness matrix for the element 1 and element 2. So first of all we will find out the stiffness matrix for the element 1, that which is having U1 and U2 displacement, and K1 is stiffness matrix 1 for the element 1, and F1 F2 is force for the node 1 and 2. So stiffness matrix for the element 1 is equal to K into U is equal to F. This is the standard formula. So K is nothing but for the element 1 is K1 minus K1 minus K1 and K1. This is the K matrix for the element 1. Then displacement matrix, that is U matrix, U1 U2. Element 1 is having 2 node, that is U1 and U2. Displacement for element node 1 and node 2 is equal to force, that is F1 and F2, force at node 1, force at node 2. So this is the stiffness matrix equation for the node 1, element 1, and same for the element 2 is K2 minus K2 minus K2 K2. This is the stiffness matrix for the K. Then U2 U3, this is the displacement matrix for element 2 at node 2 and node 3, and force 2 and force 3 for the element 2. So these are the stiffness matrix formula for the element 1 and 2. So we have to find out the global stiffness matrix for this whole element, that is a capital K is equal to K1 plus K2. So we have to do addition of these two matrices, so we will get the global stiffness matrix. So capital K is equal to whatever that first stiffness matrix is there, that is K1 minus K1 minus K1 K1. So we have to add second stiffness matrix into the first stiffness matrix. How? So last element of the first stiffness matrix plus first element of the second matrix. So whatever that first element matrix is a 2 by 2, second is a 2 by 2. So global stiffness matrix we will get in the form of the 3 by 3. So we have to just add element of the first element of the second stiffness matrix into the last element of the first matrix. Now you can see here we are going to add first element of the second stiffness matrix to the last element of the first stiffness matrix, and remaining parameter, that is the C13 and R13 0. Okay, likewise same second displacement matrix U1 U2 U3 is equal to F1 F2 F3. So this is the standard formula stiffness matrix, global matrix for this given problem. So by applying boundary conditions above, simultaneous equation can be solved. Find out the unknown like displacement U. So once we know the displacement from the strain, can be easily find out strain 1 element 1 is equal to U2 minus U1 divided by L. So strain at node 2 element 2 is equal to U3 minus U2 divided by L2, change in displacement and original displacement. So that from this we will get the strain value, and from that strain value we will get the stress value. Sigma 1, that stress at node 1 is equal to E1 into strain 1, stress 2 is equal to E2 into strain at element 2. So from that we will get the strain value and stress value. So this is the derivation and standard formula for the structural analysis of the one dimensional bar element. So we will see a simple example first, that is calculate the displacement and stress in given below. So there is one bar is there, one step, one end fixed, one end free. We are applying 100 Newton force at one free end. Cross section area is 20 mm per square mm. Length of that bar is 10 mm, and Young's modulus value is 200 into 10 raised to 3 Newton per mm square. So we have to find out, this is only one element, so we have to find out the stiffness matrix for this element. So standard formula for the stiffness matrix, that is a AE by L into our matrix. Here element is only one, so that its standard formula is 1 minus 1 minus 1 1. So this is the standard formula for this element. So we have to put the values of the area of cross section, Young modulus, length. So next step, that is a K is equal to area of cross section is 20 mm square into Young's modulus 200 into 10 raised to 3 divided by length 10 into 1 minus 1 minus 1 1. So this is your global matrix of stiffness matrix for the given formula. So next formula, we have to find out the unknowns, displacement and stress value. So for that, our standard formula for the structural analysis, that is a K into U is equal to F. K matrix is already we have known. So K into U is equal to F. K 10 raised to 5 into 4 into minus 4 into 4. So into U, for this single element having two nodes, there is one node, displacement U1 U2. So Second matrix is displacement matrix, that is u1 u2 is equal to force matrix f1 f2. So for this problem at node 1 displacement here that bar element has fixed that displacement is equal to 0, and second element node we have to find out the displacement, that is u2, and f1 that is a fixed end force is considered as a capital R, and free end we are applying 100 Newton load, so that is our 100. So we have to put the values of this all in this equation, then we will get the 10 raised to 5, 4 into minus 4, 4 into u1 displacement 0, then u2 we have to find out is equal to f1 is R, then f2 is equal to 100. So from this equation matrix we have to form the equation. First equation we are going to form 10 raised to 5 into 4 into 0 minus 4 into u2 is equal to R. This is the equation first. Second, 10 raised to 5 into minus 4 into 0 plus 4 into u2 is equal to 100. So from these two equations we will get u2 value and R value. So from that we will get u1 is equal to 0 mm, u2 is equal to 25 into 10 raised to minus 5, and R is equal to minus 100 Newton, that is action is equal to reaction. So whatever we are applying on the free end force, that is equal to only opposite minus sign at the fixed end, reaction is there. So we have to find the first strain value at element 1, that is equal to u2 minus u1 divided by L1. u2 is 25 into 10 raised to minus 5 minus 0 divided by L10. So your strain value is 25 into 10 raised to minus 6. And from that strain value we will calculate the stress value. Stress is equal to Young's modulus into strain, 200 into 10 raised to 3 into 25 into 10 raised to minus 6, that is a 5 Newton per mm square. So from this problem we will get the displacement at node 2 25 into 10 raised to minus 5 and mm, and stress is equal to 5 Newton per mm square. So this is the first simple problem. Second problem, which is having two elements, stepped bar elements. In that area of cross section of the element, first is 400 meter square, second 200 meter square. At free end we are applying 20 Newton force, each element having 200 mm length, and Young's model is 200 GPa. So first of all we have to find out the first stiffness matrix at node 1, K1 is equal to AE A1 E1 divided by L1 into 1 minus 1 minus 1 1. So we have to put the values. A1 is 400 into E 200 into 10 raised to 3 divided by 200. So if we will get the first K1, it is 10 raised to 4 into 4 minus 4 minus 4 4. Same we have to find out the K2 for element 2, A2 E2 divided by L2, 1 minus 1 minus 1 1. So from that A2 is for area of cross section for second element is 200 into Young's modulus 200 into 10 raised to 3 divided by length 200. So K2 is 10 raised to 4, 2 minus 2 minus 2 2. So from this two matrix we have to find out the global matrix, that is a capital K is equal to K1 plus K2. So capital K is nothing but we have to add first element of the second stiffness matrix into the last element of the first stiffness matrix. So we will get the 3 by 3 matrix, that is a 4 minus 4 0 minus 4 6 minus 2 0 minus 2 2 into 10 raised to minus 4. That is your global stiffness matrix, and from that we have to find out our unknowns, that is a displacement and stress value. For that we have to know the standard formula K into U is equal to F. Already we have calculated the stiffness matrix, that is global stiffness matrix, into displacement matrix U is equal to F. So 10 raised to minus 4 into 4 minus 4 0 minus 4 6 minus 2 0 minus 2 2 into displacement matrix U1 U2 U3 is equal to F1 F2 F3. So in that U1, that is a displacement at fixed end, that is a 0, u2 we have to find out, u3 you have to find out. In next, force F1 is equal to R reaction, F2 we have to find out, sorry, F2 we have to consider as 0, and F3 is, we have to know, that is a 20 Newton. So from this equation we have to create three equations, that is the first 10 raised to 4 into 4u1 minus 4u2 is equal to R, 10 raised to 4 minus 4u1 plus 6u2 minus 2u3 is equal to F2 is equal to 0, and last 10 raised to 4 minus 2u2 plus 2u3 is equal to F3, that is 20. So from these three equations we have to find out the u2 and u3 values. So solving these above equations, we will get u2 is equal to 0.5 into 10 raised to minus 3, u3 is equal to 1.5 into 10 raised to minus 3. So we get displacement value u1 is a 0 at a fixed end, u2 is equal to 0.5 into 10 raised to minus 3, u3 is equal to 1.5 into 10 raised to minus 3 mm at node 3. So from this displacement we have to find out the strain value at element 1 is equal to u2 minus u1 divided by L1, u2 is equal to 0.5 10 raised to minus 3 and minus u1 0 divided by L1 200. So our strain at first element is 0.25 into 10 raised to minus 5, and strain at node 2 is equal to u3 minus u2 by L2, u3 is 1.5 into 10 raised to minus 3 minus u2 0.5 into 10 raised to minus 3 divided by 200. So strain at element 2 is equal to 0.5 into 10 raised to minus 5. So from this strain value we have to find stress value. Stress as element 1 is equal to E1 into strain 1. So stress 1 is equal to 0.5 Newton per mm square. Stress 2 is equal to E2 into strain 2. So stress at element 2 is equal to 1 Newton per mm square. So this is the simple example of the two-stepped bar. So next, which is having three-stepped bar. So same as like previous, just we have to calculate the stiffness matrix for the element 1, element 2, element 3. So formula for the standard stiffness matrix is AE by L into 1 minus 1 minus 1 1. So from this we have to calculate first K1 for first element, that is AE by AE E1 by L1 1 minus 1 minus 1 1. So whatever that area of cross section for the element 1 is 50 mm square, length for the first element is 10, and angle modulus is 200. So first K1 is equal to 10 raised to 5 into 1 minus 1 minus 1 1. For same, K2 for element 2 is equal to 10 raised to 5 4 minus 4 minus 4 4. Third, K3 for the element 3 10 raised to 3 2 into minus 2 minus 2 2. So from this three stiffness matrix we have to form a global stiffness matrix, that is a capital K is equal to K1 plus K2 plus K3. So already we have known that K1, K2, K3. So we have to add these three global matrix and then we will get the 4 by 4 global matrix. So at the time of the addition, so as per our rule, so at the time of the adding, the last element of the first stiffness matrix will be added to first element of the second matrix and last element of the second stiffness matrix into the first element of the third stiffness matrix. So we will get our final global stiffness matrix, that is capital K is equal to 10 raised to 5 into 10 10 0 0 minus 10 14 minus 4 0 0 minus 4 4 plus 2 minus 2 0 0 2 2. So remaining element that will be considered as 0. So this is your global stiffness matrix for this given problem. So our standard formula for finding out the displacement and stress, that is K into U is equal to F. K matrix we have already found out. U is your displacement, u1, u2, u3, u4, and force, that is f1, f2, f3, f4. So in that, u1 is equal to 0, displacement at fixed point, u2, u3, u4 we have to find out. f1, force at fixed range, that is equal to capital R, reaction. f2, f3 is 0, and f4 is 250 into 10 raised to 3 Newton. So from this matrix we have to form the equations. First equation, that is 10 raised to 5 minus 10 u2 is equal to R. So from this matrix we have to form the 4 equations, and from this above equation we have to find out the u2, u3, u4 values. So u2 is equal to, we will get 5 into 10 raised to minus 5, u3 we will get 17.5 into 10 raised to minus 5, u4 is equal to 42.5 into 10 raised to minus 3, and R is equal to minus 50. So this is the displacement values, and from that displacement value we have to find out the strain value. First element for strain value, E1 is equal to U2 minus U1 by L1 is equal to 5 into 10 raised to minus 6. Strain at element 2, U3 minus U2 by L2 is equal to 12.5 into 10 raised to minus 6. And strain at element 3 is equal to U3 minus U2 by L3, U4 minus U3 by L3 is equal to 25 into 10 raised to minus 6. And from this above strain value we have to calculate the stress value. Stress at element 1 is equal to E1 into strain 1, it is 1 Newton per mm square. Sigma 2 is equal to strain at element 2 into E2 is equal to 2.5 Newton per mm square. Stress at element 3 is equal to E3 into stress E3 into strain at element 3 is equal to 5 Newton per mm square. So this is the third example of the structural analysis of 1D bar element, which is having 3 elements. So these are the simple example of the structural analysis. So we will see next, that is a thermal analysis of the one dimensional bar element. So in that we have to form just Fourier's law for the heat conduction. So we know that the equation for that Fourier's law, capital Q, that is heat conduction, is equal to minus K into A dt by dx. So this is the equation first of the Fourier's law. So we know that already we have derived the structural analysis formula, that is F is equal to K into U. So from these two equations we will get the third equation, that is a capital K into capital T is equal to Q. And this is the equation for the thermal analysis of the one dimensional bar elements. So K into A by L into 1 minus 1 minus 1 1, that is a stiffness, first K matrix. Then second temperature matrix, that is a T1 T2, and is equal to heat transfer rate, that is Q matrix Q1 Q2. So we will see the first simple example. Consider the temperature distribution through its composite wall shown in figure below, which is composed a layer of the insulation sandwich between two walls. Use of the FEM to predict the temperature T2 and T3 at the interfaces and heat flow per unit area through the wall. So now you can see there is one composite wall is there, A section which is a steel and B section which is a insulation. For the thermal conductivity for this two sections are given. For steel, 18 to 10 raised to minus 3 watt per mm degree centimeter, and for insulation thermal conductivity is 4 into 10 raised to minus 3 watt per mm degree centigrade. So temperature at first point, that is 150 degree, and temperature for the last 4 point element node, which is 30 degree centigrade. So given data is a T1 and T4, L1, L2, L3, we know 10, 20, 20. We have to find out the temperature at node 2 and temperature at node 3 and heat transfer at node 1 and node 4. So from this we have know the formula for the thermal analysis. Assuming the unit cross section area for the each element is 1, that is the area of cross section is equal to 1. So we are going to start from the thermal conducting matrix for the stiffness matrix for the element 1, that is K1 is equal to K3, because K1 and K3 is same for the steel material. Okay, so K1 is equal to K3 is equal to Ka into A. Ka means thermal conductivity for the first steel material into cross section area A divided by length LA into 1 minus 1 minus 1 1. So thermal conductivity for the first steel material is 80 into 10 raised to minus 3 into area of cross section is 1 divided by length 10 into 1 minus 1 minus 1 1. So stiffness matrix for the element 1 and 3 is equal to 10 raised to minus 3 into 8 minus 8 minus 8 8. So this is the for first element. For the second element, stiffness matrix is 10 raised to minus 3, 0.2 into minus 0.2 minus 0.2 0.2. So we will get the final global stiffness matrix, that is capital K is equal to K1 plus K2. So as per our rule, we have to add this two matrix into the single matrix. So last element of the first matrix will be added into the first element of the second matrix, that is a 8. So we will get the global matrix, that is capital K is equal to 10 raised to minus 3 into bracket 8 minus 8 0 0 minus 8 8 plus 0.2 0.2 0 0 minus 0.2 minus 0.2 0.2 plus 8 minus 8 0 0 minus 8 plus 8, bracket complete. So this is our global stiffness matrix for this problem, composite wall. So we know that the formula for the thermal analysis, that is a K into capital T is equal to Q. So we have known that the stiffness matrix, global stiffness matrix, that is a 10 raised to minus 3 into bracket 8 minus 8 0 0 minus 8 8.2 0.2 0 0 minus 0.2 8.2 minus 8 0 0 minus 8 8 into temperature matrix, that is a T1 T2 T3 T4, in which that T1 is equal to 150 and T4 is 30, and T2 and T3 we have to find out, is equal to Q1 Q2 Q3 Q4. In that Q2 and Q3 is equal to 0, we have to find out the Q1 and Q4. So from this matrix we have to do the calculate the equations, and we have to find out the temperature as well as heat transfer value. So T2 is equal to 147.4 degree and T3 is equal to 32.85, and from that temperature we have found out the Q1 is equal to 22.56 into 10 to 3 minus 3 watt, and Q4 is equal to minus 22.8 into 10 to minus 3 watt. So this is the unknown values from this given composite wall problem. So this is the thermal analysis problem. So our analysis of the one dimensional bar in structure and thermal analysis is over. So we have to just remember the standard formula for the structural analysis and thermal analysis, and from that we have to find out the first stiffness matrix for the different element, and from that we have to form the global matrix, and from that global matrix, after finding the global matrix, we have to find out the unknown values. In structural analysis, our formula is P is equal to K into U, and thermal analysis K into T is equal to Q, and from this equation we can easily find out the unknown values. So we will see our last point, that is the introduction of latest FEA software. So there are number of the analysis software are available in market which are used for finite element method. Majority of the software work on the Windows XP. Following are major softwares used in the industry. First, that is ANSYS. It is developed by ANSYS Inc. It is USA based software and it is developed for CAE package. So field student version is available up to 32,000 nodes. So up to 32,000 nodes we can free of cost analyze this problems. Beyond this we have to pay the money for that license copy. So this is the first software. Then second, Nastran. It is developed by MSc. It is originally developed for the NASA. and nowadays it is commercially available for many of the software companies. So it is basically developed for the NASA. It will be currently available for the many companies for commercial use. Next, LS Dyna. It is developed by LSTC. It is specially used for the crash analysis. So this type of the software using for separate crash analysis. Next, COMSOL. It is developed by COMSOL. It is an engineering software formerly known as FEM Lab, which is include multiphysics. So this is developed by COMSOL, and it is basically engineering software and basically known for the finite element method lab, which is included in multiphysics analysis. Next, Hypermesh. It is developed by Alter. It is a meshing software generally used for the pre and post processing. So during the after the modeling, during the analysis, this type of the software using for the pre and post processing analysis, and this is basically a meshing software. Next, Range software. It is a multiphysics FEM software which is available free of cost. It is a post of the LS Dyna. Okay, it is a part of the LS Dyna. So it basically it is used for the FEM analysis in multiphysics, and it is free of cost. Next, CodeAster. It is developed by the EDF. It is open source software used for the structural mechanics. Basically, it is used for the structural mechanics analysis, and it is a open source. Next, FEMAP. It is developed by the Siemens, and it includes pre and post processing only. It is a commercial software. So it is developed by the Siemens, and it is including only pre and post processing. Next, Patron. It is developed by the MSc. It is a pre-processing and post-processing software which is supported by Nastran. It is also using for the pre and post-processing analysis, which is supported by the Nastran software. So these are some example of the latest FEM software. So this is last point of this our finite element method chapter. So our chapter number 3 is over. Thank you so much.